Great. So our next speaker today is William Kennington. He'll be talking to us about system resilience for OpenBMC. So William is a software engineer at Google who's working on the OpenBMC upstream project. He maintains some of the core system components and has been contributing to improving the resiliency and the proper functionality of OpenBMC.
Great, thanks, Benjamin. So yeah, as he said, I'm working on GBMC at Google, which is our internal distribution of the OpenBMC platform. And as someone who's been working on bringing up servers now for 3-ish years and then focusing more on BMC components nowadays, having things fail on you is something that just inevitably happens when you have lots of machines. And so we need ways of resilience so that in the case of those failures, we can either completely recover or we can do something that acts as a fallback that kind of like gets us far enough along that we're able to do critical functionality without maybe servicing extraneous needs, but we're still able to have the system operate in a functional state. So what do these things look like? So our background, anyone who works on these platforms at Google, comes from having many machines with a focus on automation and monitoring. Because you have so many machines, you can't go in and manually intervene anytime something goes wrong. You'd like to maybe for some of them, but you definitely don't want to be at the point where you have someone going in physically and having to push and pull a server to restart it. You want to have all of your tooling available so that you're able to go and to fix machines that are broken in the fleet without having to do anything by hand or going in one-off and doing those things, because you may not even have access to those machines, right? Like in a lot of cases, we deploy machines into production and the developers who work on these things that are able to dig in and debug the issues may have no access to that machine or that BMC or any of the data there. And so we'd like, in general, for all of our failures to be self-recoverable. We'd like these things to be self-healing. We really never, ever, ever want to have to intervene. Even if it's the case that we're losing mutable data, so we actually have settings data written to the BMC, we really don't actually care about that data that much, so much that we'd rather have the machine fail completely. We'd rather it limp along and try and get back into a usable state and maybe go through some kind of automated repairs flow. And so that kind of hits that next point. And it's worth noting that for us, we have very limited access to the BMC in general. Our BMCs really only have IPMI access. There's almost no form of out-of-band. You don't have SSH, you don't have Redfish, you don't have any of these things. So everything that we do has to be implemented as an IPMI command, and we really don't want to extend the IPMI specification so much that we're able to do things like read and write to the file system and SSH tunnel through IPMI or something really bizarre and gross. And so we want to sort of adapt as much of IPMI as we can to our troubleshooting needs without going too far and getting ourselves way too ingrained in building our own custom stuff for IPMI. And this makes it really hard to debug issues on the BMC because right now we have very little access to read a lot of the data that the BMC generates. So the BMC generates logs in journal D or in any of the system D mechanisms. And then those logs have no SEL representation. Maybe we have some things that do log SELs, but that's the only information we're able to actually extract when we see an error. So the OpenBMC system, if you're unfamiliar, is designed as kind of a whole bunch of microservices and then some routing functionality that allows the host system and out-of-band network to access it. In our case, we kind of ignore that out-of-band network and network transport driver and Redfish and those things for now because we don't deal with that so much as we deal with the IPMI going to the host system level. So you'll see we're actually running a fairly powerful microcontroller. We're running something that runs Linux, and it's running systemd and user space and all of our microservice daemons. I didn't list all the daemons because, quite frankly, if we listed all of them, there would be way too many, and this would become even worse of a spider web in there than it already is. But I did try and give some representative examples, like having temperature sensors. We have a whole bunch of those daemons that are able to talk to the hardware mon drivers in the kernel, which then go out and talk to probes and DIMMs and talk to the CPU, those sorts of things. And you have fan controllers where you have fans in the system. So your BMC is monitoring the fans and it's issuing fan control actions and it's trying to set fan curves based on the temperature data it's getting. And so you have the fan control daemons. Those actually do talk to the temperature sensors because it does need to know for the different thermal zones what the fan configuration needs to be based on the thermal feedback it's getting. And then you have daemons like the host watchdog, which actually has no outside communication. It's not talking to the kernel, not talking to these external devices. It's purely talking over dbus to the IPMI daemon and giving the host system a way to pet this watchdog. And in the worst case, if the host stops responding, then it's able to go and kill the host system and bring it back up. And then you have network settings and user manager. These are also things that live on the BMC, but they have a sort of mutable state associated with them. So when the user or the external agent on the host system comes in and wants to change the BMC's network configuration, it will eventually get written through the IPMI router into that BMC network settings daemon, and that will persist something onto the disk. And sort of the core theme here that you'll see is that if you ignore the network components, you really have these single points of transit to the outside world. You're communicating only to the host system through the transport driver, that could be the KCS bridge or some kind of block transport mode, through the daemon that handles talking to that specific type of transport, and then through that IPMI router, which we call IPMID. And that then proxies into all the services. But if any one of those things fail, you now have no way of talking to the outside world. The BMC is completely isolated, and as far as you're concerned, it's bricked. So what are some problems that we have that we don't have resilience in place for? So if our service locks up and just decides to not make any new progress, then we have no way of servicing new requests. Let's say your network settings daemon tries to parse some kind of IPv6 subnet mask for an IP that is just a single IP, and while it's trying to parse that into a net mask, it goes into an infinite loop. And now none of the other requests coming into your network daemon have a way of being serviced. That's a huge issue, and it's something that a resilience feature could actually solve and would be able to restart that service. How about pathological devices? These things exist, right? Our motherboard is covered in devices that talk over I2C, talk over one wire, all sorts of protocols, and they all inevitably have some sorts of pathological behavior in certain cases where they will just make the bus take forever and just maybe not respond to messages at all. Or you have C++ code. It would be really nice if we were writing in safe languages like Rust or Go or something, but right now we're not. I mean, that's a dream. It'd be awesome. But we're writing a lot of code in C and C++, and there's a lot of easy ways to create undefined behavior, and there are ways to crash the code, and it happens. If you introduce exceptions in C++ and you're not catching them, for example, that's something we did, and it did cause a lot of daemons to crash, and it's really nice if you can recover from those crashes. The IPMID being unavailable for long periods of time, this makes the BMC in our instance look like it's down. And so we really want to make sure that we have some mechanism to guarantee that all of our daemons are making forward progress. Because if you're not making forward progress, then you have no way of being able to service any new requests and perform critical features. Corruption in the read-write file system. File systems are hard. Devices that store data are notoriously bad at storing data. And this is something where we have all sorts of, we've seen this manifest in all sorts of ways in the past. One of these ways is if the superblocks for JFS2 get corrupted, then you have no way of being able to boot the BMC because this read-write file system overlay is completely borked and unable to run. And same with filling up the file system. You need to make sure that you have constraints in place, quotas, to make sure that generated data doesn't take precedence over mutable data and things that are actually critical to system function. And then you have corruption of runtime services or memory. This is fairly straightforward. This is basically use ECC memory. It's something that is available on all the BMC platforms today, and it's something that you should actually make sure you enable, because when you deploy enough of them, you'll end up eventually seeing bit errors in your memory. So I'd like to start with the systemd focus because we're so heavily systemd based. I'd like to highlight some of the things we're already doing and then some of the features we could be using that I'd like to see used more that would actually fix some of the bugs that we've seen in the past. So the restart equals directive. This is something where when you create a service definition in systemd, you can tell it that anytime it sees a failure or just always, anytime the service exits or changes state, go back and restart it so it ensures that the thing is always running. You can perform actions if the service fails. So you could say, if the service fails, it's a really critical service. It's the IPMI daemon. It's the only way into the system. Make sure that when it fails, you just reboot the system and try again. Just bring everything down, bring it all back up. And you can implement fallback services with those same actions. It actually allows you to start any arbitrary systemd unit or service. Watchdogs, great thing that systemd provides. You can have a notify socket passed to you, and that'll allow your service to be watched by the service manager. And if you stop making progress and you stop petting that watchdog, then you'll be able to have the service automatically restarted for you. And then systemd also provides the option to control the system watchdog, which I don't think is enabled by default on all of our platforms, and it should be. This is sort of that same thing where if for whatever reason systemd stops making progress itself in monitoring the system, then the system's able to kick itself and restart. And really just check out the man pages for more. The man pages for systemd are fantastic. They cover a ton of different options, and there's always more being added, and so this is definitely not comprehensive. So service restart, let's say we have a crashy daemon, and I just call it crashy D because I'm boring. And this thing always just exits at some point during its runtime. And so what we want to do is we want to make sure that anytime we see the bad exit, you know, let's say it gets sig term or something randomly from somewhere else and it breaks, or it's just has some kind of memory exception. We want to make sure that we restart that anytime we see those conditions. This is actually already pretty widely implemented in OpenBMC. If you go and you look at the service definitions in our repos, you'll see that the restart equals something. Usually I think it's always for our daemons, but On failure is also a pretty reasonable option, especially if you don't expect the success condition to ever happen, the exit code of 0. And this is nice because it requires no code changes. All you have to do is update your systemd service schemas. And it really is helpful if you have intermittent crashes, but it's not great if your code crashes immediately at startup continually, because that would just cause the system to continually try over and over and over and over again to restart. Now, systemd isn't actually that naive. It does actually have a limit. I think it's like 5 starts every 30 seconds, and there are actually 2 parameters that control this that you can tweak for the service. So there's the start limit interval and there's a start limit burst. And that kind of controls how often it will allow the service to be restored before it says, hey, this thing isn't going to start. Why would x plus 1 start if all x times didn't start? Let's just kill it and say it failed. And then you report that to the journal. And if you query the status of the service, you'll see it in a failed state. And I think this is something that's actually really important to keep in mind if you're designing daemons that manage daemons. So in our case, we have a network settings daemon that leverages systemd networkd to do all of its communication. And so anytime any of the configuration changes in the network settings daemon, it goes to systemd networkd and it writes out the files and it restarts it. But if you do this too many times, so if you issue a bunch of network settings changes over IPMI, and it doesn't coalesce them into one change, then it will actually end up restarting the service a bunch of times in a burst, and you'll hit this same limit. So you need to be really careful. If you do expect a daemon to restart and have changed behavior, you need to reset these counters on the thing, and it's something that we actually added fairly recently to the network settings daemon. And then there's just unit failure options. So you have your crashy daemon, and it's so important to you that if you ever see it fail, so it tries to restart it a couple times, but eventually it hits that burst limit and then it fails. And on the failure action, what it will do is it will reboot the system. So you have a couple of things you can do here. They're fairly hard-coded. One of them is power off, one of them is reboot, and the other is kexec into a different kernel. So it's really like you're just halt the whole system, go and do something else type actions. And there are different severity levels. So in this case, this is at the force. You could say immediate, so it won't even sync the file systems. It'll just kill, it'll just trigger the watchdog on the system, CF9, whatever. It'll just kill the whole thing. And this is great for your very critical daemons. I would avoid trying to implement this widely, because if you have something that's not critical, like you have your temperature sensor daemon and it's monitoring a temperature and it crashes, who cares if the temperature for some probe on the board decides to die off? You don't want to have the whole BMC restart and then wait a whole 2 minutes or something for the BMC to come back. You could very easily cause yourself a denial of service of the BMC, and then you wouldn't be able to update or do anything anymore. There's also the ability to do a fallback action. So this is like a more generalized version of the previous action. And so instead of saying, I want to reboot the system, you could say, I want to start a different service that maybe is less crashy. So in this example, we have a less crashy service. In the real world, we could use this with IPMID. We could have an IPMID that's like a fallback or a recovery IPMID. And then in that case, you would design it to be very small, only handle the critical functions that you need, and make sure that it's not servicing anything that's extraneous that might cause it to crash. And so by reducing the code surface in your less crashy fallback, then you'll be able to recover. It's important probably that if you do fall back into one of these modes, you have some way of knowing. Typically, like if it was something like IPMID, you would just start seeing all of the commands that you don't need erroring out with some non-implemented type error or just a system error. And this, I think, in general, would be very useful, but it does require you to create code. So it does not require code changes to your main daemon, so your crash ED or whatever. But if you were going to implement some kind of fallback, then it would actually require you to make a whole bunch of new code or create some kind of build options to be able to reduce the functionality or code service of the original crashy daemon. And for non-critical services, this may be too much overhead. You may not want to provide all of these different options. But I think for something that's really core to your functionality and has a whole bunch of extraneous code that you don't necessarily need to recover a system, you may want to consider doing something with a fallback here. And then the other thing that systemd provides is a service watchdog. So let's say you create the infinite loop in your service again, and the service stops making progress, it stops responding on dbus, and that causes the whole system to become really sluggish and start timing out all the dbus requests to that service and just become generally unserviceable for that specific action. If you have a service of type notify, and you get this notification socket passed from systemd, the service can request systemd and it can say, hey, enable a watchdog with a certain timeout. So you say, you send it this variable called watchdog usec over the socket, you pass it the actual usec parameter after. It's like a key value pair thing, but it's all straightforward if you look at the man page for SD_notify, or you just use something like SD event or SD event plus. You pass it this usec timeout, and then every couple periods in that interval, you go and you pet the watchdog. So as long as you're petting the watchdog maybe 3 times as often as your timeout, you should be okay, and it'll know that your service is continually making progress. And so if you're using an event loop, something where any one transaction could cause the entire event loop to stop, this will protect you from those cases, and it'll be able to restart the service anytime the watchdog stops being pet. Like I said, if you're using SD Event or SD Event Plus, this is built in. All you have to do is say SD Event enable watchdog, and it'll enable the watchdog with the timeout you give it, and it will handle all that for you. It has like an internal event source that's able to be run every so often in the event loop and make sure that that is actually going and updating your watchdog. There's no reason you couldn't retrofit any other event loop to support this. I know we have a lot of ASIO code that's out there, and you could plumb this in as some sort of source within the ASIO framework that just goes and makes sure on some kind of timeout, it runs SD notify and it pets the watchdog for you. So this is kind of a minor code change, but I think it's fairly easy, especially if you're already using one of the standard libsystemd event loops. And so I think it's kind of a win in the short term. And then this is sort of a harder problem. We have a whole bunch of single points of failure, as we're seeing in that diagram. So I like to pick on IPMID here because this is the one that has a lot of code, and it's one of the core critical pieces that we need to perform like system resets and get the controller info and do updates. And it ends up having a myriad of issues when we deploy it widely and start really stressing it out. And so this is something where if you have a whole bunch of communications happening to a single daemon on your bus, and it performs blocking calls, it's only able to service one of those things at a time. If you're not using POSIX threads or something like that, anytime you block, you're preventing any other work from being done. And so your daemon is waiting on IO for something that it doesn't need to actually wait for. It could be servicing other requests that have nothing to do, aren't actually mutually exclusive to the request being processed. And it means that if you have a huge queue of IPMI traffic that's servicing sensor reads, and your sensors are for some reason taking forever to read because you have some wonky sensors or the kernel's kind of busted, or who knows. So there's a whole bunch of reasons why your sensors might be flaky. They are external devices after all. But that means that your host watchdog isn't able to be pet because your IPMI queue is backed up by all of these sensor transactions. And so eventually what happens is the sensors take all this time, the watchdog never gets pet, and the watchdog eventually trips and you're in all sorts of trouble. Or it just makes it really hard for you to reset the host, or it makes it really hard for you to upgrade the system because those upgrade commands take forever to start timing out. And so it's really important in general that we sort of reduce these points of congestion. And I think that we are doing a pretty good job. We are kind of working our way there. And this isn't exclusive to just the system services that we designed. This also includes the kernel. Kernel drivers have probe functions. And it turns out that if the kernel drivers don't specify that they are async compatible, their probes run in serial. And if you set up a device tree that's processed and starts probing at the beginning of boot, what happens is your probe functions actually hold up your init and everything else in the system. And so if you have some wonky voltage regulator that tries to report your voltages, and you need that probe function to read the version of that voltage regulator to know how to handle it, then what ends up happening is your boot gets held up for 200 seconds because it's trying to read the version of this voltage regulator and not doing anything else. And honestly, if you want to be able to talk to the IPMI daemon or manage some of the BMC services or manage host power control or deal with the watchdog, none of that is actually relevant to you. You don't need this one sensor that has no relevant information to the critical paths in your boot. And so in general, I think having the kernel do more things asynchronously in terms of probing would be really nice. And so this kind of boils into the next point, which is async request handling. I think we're getting there. I think we're sort of doing a good job, but it's one of those things where as we start having more of these applications that are using event loops, we need to make sure that we're never blocking on calls that we don't need to. So if you're making dbus calls, you really ought to make them async as much as possible. That way, other work that isn't actually dependent on those calls being made can be done in the background. And so you can actually effectively thread out to doing multiple requests, but really you're doing it in a single thread. And this is really a big issue when you have these aggregation points like IPMID. So you don't want your sensor calls that are going to phosphor hardware mon to block up your calls that are setting network settings. Completely irrelevant and not actually necessary. And in general, I would say those are a less critical path than being able to upgrade or reset the system or get the version, make sure IPMI is alive, do the watchdog actions, those sorts of things. And I think the state machine type of async is a good place to be in general. I really wish we had something like Rust where they build in the state machine asynchronous behavior for you, but we're not there yet. I don't know how hard it would be to actually get it working. I got a hello world in Rust working on the BMC and it was like 8K and I was really happy, but I don't know how scalable that'll be once you start including a whole bunch of libraries that end up being statically linked into single Rust binaries. And so that's something to investigate. But I think going down the path of using SD-Event or ASIO or any of those things is generally good, and it'll allow us to be more available and process more things simultaneously. And this leads us kind of into file system issues. So we've had a whole bunch of trouble in deployment where spy devices or drivers or anything in the stack that's under the file system ends up causing some kind of corruption at the block level. And so what ends up happening is in the BMC right now, the way OpenBMC is architected, we have a read-only file system and we have a read-write file system. Unfortunately, they're overlaid on top of each other. So the first thing it does before it calls into init is it tries to mount both of them. And so if for some reason your BMC decides to corrupt the read-write portion in some way, like the JFS2 metadata just gets corrupted, the CRCs error out, and it decides to not mount, then your BMC is completely bricked, unbootable. You have to go in, you have to do a chip swap or reflash the BMC or something along those lines. And so maybe in the best case, all that happens is you have data corruption. Ideally, you'd have file systems that don't allow that, but we're not there. JFS2 just has no checksumming of your data. And so if you write partial amounts of data, then that may be what you get back. You may get back complete garbage because the spy chip just hates you that day. It's kind of what you have to deal with, unfortunately. And then again, the worst case, metadata gets corrupted and you're unable to mount. And so you probably need some way to recover from that scenario because you're going to end up doing chip swaps otherwise. And this is kind of a problem. And then you also just have the file system becoming full, something that's not great. And so one thing would be more resilient file systems. That'd be really nice. Maybe we have built-in data integrity, something like ButterFS or ZFS. I know some of us in the audience maybe not so hot on ButterFS, and these two file systems aren't great solutions. I think in general on the BMC, because you have such a small amount of flash and you don't have a ton of RAM to begin with. And so these are fairly heavyweight solutions that we may not actually be able to leverage. But I think if we just try, I think if someone were to build something, it may not be fully POSIX compliant. It may be some kind of key value store. I think that could be useful. If there was some way that we could provide really good data integrity in the small amount of space, even if it's not terribly performant for random access, I think that would be really nice. And I think in general, having something where we reduce the dependence on the mutable overlay would be good, because that blocks us really early in the boot process and it locks us into needing that read-write file system to be available. If we can defer to later in the boot process, opening up that read-write FS and then having fewer dependencies on it, I think that would be good. The systemd folks propose a stateless file system layout, and I don't really necessarily care to be tied into that specific layout, but I think picking something where you have stateless components and then you have stateful components that are managed separately and not everything depends on the stateful parts, I think that would be really helpful because it allows you to get farther into the boot process before you have to deal with the fact that your read-write storage is actually corrupted. But this would require some storage redefinition. I'd like to actually start taking on this work and see how bad it would be if we just don't have a read-write file system at all, see what actually comes up, start adding things like varlib and varlog and etc to that read-write space and see how much farther we get along, those sorts of things. But more importantly, if your file system is completely corrupt, you need to do something about it. And so I think providing an image feature for just auto-purging if the file system is corrupt is a really good idea, because otherwise you're just going to get no feedback from the system. If you're not monitoring the serial console or you have some other kind of like out-of-band mechanism that's very low level to know if the BMC is hitting this really early on in boot, you need it to just say, okay, the mutable data is not really that important. We really want to recover the system, get it back up and running, and then we can reprovision things as necessary. And then once you do find that corruption and you eliminate it, you purge it, you do something about it, you need a way to communicate that that's what happened, because you need services to make sure that they reprovision their settings. We would like to be able to emit logs, but it's not that straightforward if you're doing it this early in boot, because your systemd journal won't have a place to persist its journal. It's not even actually running at this time. And so we'll need to come up with some mechanism for communicating up the stack that we hit file system corruption and we're kind of resetting from factory defaults. And I think in general, our applications need to become better at handling corrupt data. Do we just ignore it and emit warnings? I think right now in a lot of instances, you'll see that applications, when they get data off the disk that is kind of inconsistent, especially from the read-write portion, they'll do something weird, they'll crash, they'll handle it poorly. And I think in general, they need to be more, they need to hard panic less often and do things that tell you that the data is broken, but they need to just kind of ignore it and move on and try and recover back to a sane working state. And then another thing I noticed pretty commonly is that we're not implementing good write consistency. We could use proven database formats, which I realize aren't actually perfect. Using something like SQLite will make it better, but it's not necessarily a given that it will work perfectly. And then if you're writing text files that don't have some kind of journaled schema or anything, you need to make sure that you actually write those separately and don't overwrite the file that you're actually intending to update, because some of the writes may not actually persist to disk if you have power loss or something along those lines. And so you need to make sure that you're writing somewhere else and then using an atomic move over the file so that it's just a metadata update that flips the data into place and you don't have partial writes going on into the file. And then not everyone has similar needs. Maybe we want it to auto recover and blow away all the settings willy-nilly, and that's okay. But others may have use cases where they just want the BMC to up and panic because they want to be able to diagnose, go in, root cause the issue, and be able to see what happens, and they don't want the file system to be blown away. And so I think that presenting these things as options at build time or as runtime, really build time configurables, because if your mutable state is completely broken, you need some way to determine what action you're going to take. And so having a build time configurable would be really nice for that. And then what about free space? I think a simple solution to this is just implementing some kind of quota system. This is something that we don't currently have, but I think would be really nice, especially for those of us that are logging our journal to a persistent medium. Right now, I think our distribution doesn't do any of this. We put almost everything in RAM because we don't trust ourselves with not filling up the read-write file system. But I think if we implement better policies, it should be possible for us to store some of that data without filling up the entire thing and making the system completely unusable. And so a trivial solution to make it more reliable would just be to say 70% of the space can be dedicated to this autofill generated data, and then 30% of the space would be used for things like user settings and stuff that's generally fairly small or has fixed sizes. And then this goes back to the monitoring question. How do we know if we're running low on space? I think right now we don't have a good communication mechanism for that, and it's something that we really need to think about and consider. Which brings us to sort of the host watchdog issues. Now, the host watchdog seems like something that's really simple to do. All you have to be able to do is set the watchdog, pet the watchdog, and stop the watchdog. And it's like 3 commands. This should be really easy. And it's something where a daemon just has to implement a timer and wait. And if it doesn't get pet, then it trips the watchdog and it says, okay, I'm going to restart the system, or I'm going to do nothing. There are a couple actions. It's not really that complicated if you just look at the spec. And it seems really useful because every platform that supports IPMI supports this watchdog. As long as your Linux kernel supports the IPMI driver you need and your watchdog stack on your Linux system supports the watchdog, then it's really easy to support for your IBM Power systems, your Intel x86 systems, and your AMD x86 systems, or your ARM systems, whatever. Doesn't matter. It's fairly ubiquitous to all of them. Whereas if you went to any one of those platforms and you wanted to use the platform watchdog, you'd have to have a separate driver for each one because they're all unique. The problem with this watchdog is the pipeline from the host all the way down to the BMC is incredibly complicated. And anytime you have all of this complication, you end up with issues. You end up with congestion. You end up with things crashing. You end up with messages that just somehow get lost in transit. And because this pipe that sends the watchdog messages down, yeah, is there a question? I'm saying the pipeline is complicated because it's not something like you have fixed hardware where it's some like shared, in this case, it's a shared communication medium. See, it's complicated in that you have a whole bunch of daemons that are handling packets along the way. You go from the host, so probably a user space daemon running on the host, into the host kernel, down to something that puts it on the platform's LPC bus, down to the BMC, which then has a driver that has to read it in. It needs a system and hardware actually to notify it that that message is even there. Then it goes into the host transport driver, then to the IPMI daemon, then over dbus to the actual watchdog that's monitoring everything. And so because you have all of those different things in the chain of critical path, it ends up being fairly complicated, and you do run into issues pretty frequently, I found at least, with our deployments. And because that communication medium is also shared with things like sensor reads or network settings or any of those things, if one of those requests times out and we don't have async completely implemented, which I think we're doing better and we're getting there, but we're not there yet, then you end up not being able to process the watchdog message when you're doing something like some really long hanging sensor read. And so both of those things contribute to watchdog trips. We really don't want the host to go down if the host is fine, but it's the BMC communication that's having a problem. We really could do something if we decide that the BMC communication channel is locking up, but it should not be killing off the host and bringing it back. That disrupts workloads, and that's generally just not desirable for us. And I think it would be really nice if we could design a simpler mechanism for this so that we're not depending on the shared communication channel. I realize we can improve that to make it better, but I think that having just like some out-of-band LPC access where you're just like reading and writing to a register in LPC and then the BMC is picking that up and the daemon is completely separate from the IPMI path would be much more ideal because it would be much simpler. And it also turns out that platform resets are hard. There's not just a single type of reset. You have warm resets, you have soft resets, you have power cycles and all sorts of things. And these actually trigger different types of behaviors on the host. And for us, maybe we don't always want a power cycle. Maybe we actually want to be able to get the machine check information off of the CPU. That requires you to do a warm reset. And that allows your BIOS then to come back and pick up all that mutable state that was left in the CPU because it was only warm reset and not cold reset. But other times you have soft resets that don't do anything, or they make the platform even less stable and they make the platform go away until it gets a cold reset. Now the IPMI functionality doesn't actually support that, but we added something called the fallback watchdog that you can configure at build time to make sure that you're able to do a cold reset in the case that the machine never comes back alive from the first one. And the fact that this is just getting more and more complicated shows that it's really difficult and probably should be left up to the platform vendor because they know what types of resets they need in order to recover the system correctly. And so I really don't think this is ever going to be quite as good as a platform watchdog, but I think sticking towards using the hardest reset you have on the host is probably a good way to go. And it's also just surprisingly hard to get perfect coverage. I spent a lot of time with the OpenPower firmware guys trying to get coverage all the way from initial boot up until the end of ski boot. And so if you're unfamiliar, they have an initial boot payload, which boots what they call host boot, and this trains memory and a whole bunch of peripheral devices. And then they get into ski boot, which does PCIe training and other link training, external stuff. And then they get into their little small stage 1 bootloader, which boots a Linux kernel or a secondary bootloader, that sort of thing. And so just getting coverage so that their firmware is supported with the watchdog was actually something that was fairly challenging. But I think it was worth it, and we're finally there, and that's good. But that's not true of all platforms. So I think right now on UEFI platforms, you typically don't get watchdog coverage until the Dixie phase of the boot. And so anything that happens before that just isn't even covered. And this can actually cause a whole bunch of issues, and the lack of coverage is not necessarily ideal. And so if you use the fallback watchdog plus having some functionality to monitor postcodes, you can kind of get watchdog functionality, and it's a little bit more reliable than the IPMI method. But then you have to fall back to IPMI once you leave. And so all of this, it's just very difficult to get this to work reliably and to not have false positives and trip your host when you don't want it to. And this kind of goes back to monitoring. I think all of these resilience features are nice to have, but you need to know that they happened, especially if they're causing you to have reduced functionality or destroy mutable data. And so we really need ways to be able to know if our data was wiped, and we need to know sort of if problems arise in general. We need to be able to see that sensors have failed and that we have recovery paths to go in and root cause that. And this, I think, will be covered more in depth by Kuhn later in the day. And so are there any questions?
You were saying that the BMC will be conducted through IPMI only. There's no other channel. There's no other.
In our case, that's not true of every system, but I think in general, it's unlikely that you're going to want to implement multiple communication channels into your BMC, right?
But right now, the IPMI doesn't support any of the debuggability.
Exactly.
So how do you?
So I think so there actually are things that we have implemented through, if you're familiar with the blobs protocol that Patrick Venture created. He also created a tool that I believe he published that allows you to just pull and read arbitrary files from the file system of the BMC. And so you could actually get journal information from the systemd journal through that mechanism by just pulling the journal file straight out and running it through a journal CTL processor locally.
So this stops the purpose of having a BMC controlling the host, because now your host is controlling.
Yeah, so in our case, the host has to be available for the BMC to be reachable, which is, it's just something we deal with. And that actually makes it even more challenging to be resilient, because now not only do you have to have the BMC working and like talk to the network, you actually need the entire host to come all the way up and have a communication channel into the BMC, which is surprisingly difficult in some cases. Yeah.
So a bunch of your file system issues will be resolved with CFS.
I know. I know. I mentioned that in there, actually. Like, it would be so nice, but I don't think ZFS works on an ARMv6 that has like no memory, basically, right?
So what's the basis for that conclusion?
Also, I guess my other question would be, how well does it handle only having like 5 megs of space on disk to work with?
I mean,
would that be possible?
I think it'd be much more possible than resolving all the problems that CFS.
I agree. I tend to agree with that. Yeah.
And I think especially if there's other interest in the.
Yeah.
You've got
No, it's definitely interesting, especially if you could do even some kind of replication in there. I mean, I realize it's such a limited amount of space.
It is, but you could do a lot of stuff. That a lot of other issues would fall out.
Yeah.
Things like the quotas.
Exactly, I agree.
You would get snapshots. You would get a bunch of things.
Yeah.
And it's a technically solvable problem, and it may be your easiest route.
I agree. Yeah. Yeah, that'd be nice.
So, have you ever thought of like having a crash day or something? Because if the BMC reboots for any reason, what is the best way to collect the data or what happened after the reboot?
Yeah, so it would be nice to have something that's able to report. I think having the systemd journal is actually a pretty good sort of way to get coverage on that, as long as it's actually persisting that out to the disk. Like, is it crashing and persisting the information out? That's kind of the question that I have. And I don't know how solvable that would be. Like, I think in general, it's not the case that the BMC's kernel dies and goes away. I think that's less common in general than just having issues with the user space daemons and then becoming unavailable.
You can still have like a reserved memory where you push the data before the crash happens.
Yeah.
And on the reboot, you can push those collect those data over the IPMI.
No, and I think that's good, and that's something we should definitely look at having for sure. Yeah. Sorry, say that again?
In your proposal, are you talking about, or are you proposing that the host agents can tap the BMC watchdog periodically to get the health monitoring? I mean, how does the BMC know if the host is kind of healthy and running?
Yeah, so that's actually kind of a hard problem, and it relies on the host correctly reporting its own state. Typically, there are frameworks on the host that aggregate a whole bunch of their own internal watchdogs and then only pet the watchdog when everything's healthy. And so the BMC, I mean, you could make it more in charge of monitoring health data for the server to determine if it should restart, but that's kind of outside of the scope of the watchdog itself. The watchdog is purely there to exist to be pet, and then when it stops being pet by the host, then it goes and performs some kind of corrective action.
Have you considered,
Yeah, for resiliency, I guess it goes the other way too. How many of the watchdog functions, take the host watchdog, for example, are implemented or backed by an actual hardware watchdog timer? Because the daemon itself could stop responding, right?
Right. So actually, it is kind of interesting because the watchdog daemon now is protected by that systemd watchdog, which should be protected by the BMC's watchdog. And so theoretically, all of those things need to continue to make progress in order for the whole system to be happy. And so if for whatever reason that host watchdog daemon, that service that's providing the watchdog functionality over the host, if that ever decided to stop running its event loop, then systemd would catch that and restart it. If the BMC, for whatever reason, ever got into a state where it completely hung up, then its watchdog would restart itself and we'd be back up again. Everything ends up relying on layers of watchdogs, basically. Yeah. Which can also cause problems, right? So.
You mentioned, I think a couple of slides ago, to implement direct access to BMC logs.
Oh, yeah.
Were you referring to like the journal D
I don't
logs?
know if I think that's down here. Yeah. Yeah, this one.
Were you referring to the journal D logs?
Exactly.
Or like the
Yeah.
message logs?
I mean, it doesn't have to necessarily just be the file. Like, file system level access is one thing, but I think that's less clean than having a way to get the metadata in a format that we sort of have a defined interface for. You could maybe just pump it out as plain text instead of pumping out the binary data that is kind of horrible to work with in journal D.
And if in a case where you don't have SSH access, how do you actually get it out? If, say, you don't have Redfish implemented on it.
Yeah, so like I said, there's a file system access mechanism through blobs that we have. So we could actually say, go grab all of it, like list all the files, enumerate them all in var log, and then I think it's var log journal actually is where it stores all the journal entries. And it's a couple nested hierarchies of directories and some binary files. But inside of that, once you enumerate those, you pull them all down to the system using this blob mechanism for transferring files and doing this read-only access. And then you may need to deal with the fact that one of them was currently being written to because it's like the current journal that it's writing. But hopefully, because the format is append only, you would have all the previous entries intact and you just have to deal with truncating whatever's at the end that got corrupted because it was partially read or something in the process.
And how frequently are we doing this?
Are we doing which?
How frequently you'll be reading these files?
It would be totally up to your monitoring solution as to how often you would want to read it. Maybe you only read it when it crashes. Maybe you just like never read it at all and you wait. That's a thing that could work.
Because we do a lot of IPMI communications for reading those.
You can block a block of IPMI. Yeah. There's all sorts of problems there. I think the nice thing is that the blobs mechanism does support out-of-band transfers. So you're really just sending metadata through the IPMI channel, and then you're able to use like PCI Express or LPC or something to do the bulk transmission of data back and forth. So at least you're not blocking up IPMI sending all the data. That is actually an option that it provides, but I wouldn't do that if the logs were huge. Or if you were sending like a big update or something to the BMC where you're going to send 32 megs through IPMI packets. It's not great.
So how do you improve the system resiliency during the BMC boot? What if the BMC fails to boot? I mean, like there are different stages, right? I mean, what if it hangs at U-boot? What if it hangs at kernel? What if it hangs?
Yeah, so hopefully you have good watchdog coverage, and those are boot failures that you don't see consistently. But if it's something that happens consistently over and over, a watchdog isn't going to help you with that. Like if you just have a crash that you hit every single time deterministically, you're not actually going to be able to recover from that without just producing new firmware and reflashing. Hopefully your QA caught that prior to you releasing that image. And so you do need separate mechanisms for machines that are going through testing that you want to be able to reflash a lot. I recommend SPI emulation for those. That would be the best way to go, just so that you don't have to deal with continually pulling chips or reflashing or that sort of thing. If you use emulation, it flashes incredibly quickly and you can recover from anything.
When you're flashing the whole 32 image, or you're flashing?
I'm sure this depends based on the image type that you have. I think with the UBI system, it doesn't flash the whole thing. It's only flashing the read-only parts that need to update. But with the flat file system, you're flashing basically everything except for the read-write part, and you're actually rewriting that in the process because you want to empty everything out and only use the whitelisted section of it. And even that actually has issues because if you read out the whole thing and you don't persist that data somewhere, and then you lose power while you're reading all the data out and then going to write it back, you lose all the data that you had and your file system becomes empty again. So we do have lots of issues that we need to think about and make sure end up persisting data as much as we possibly can in all different cases that we have. And just be very tolerant to power loss because the BMC is a component on the motherboard that the user probably doesn't really think about, I think, in a lot of cases. Maybe if you own the whole stack, you think about it more and you have instructions for, not to pull power. But realistically, depending on power not being pulled is not a great solution. You generally want to avoid that. So you don't want to have the dependence on needing to be powered to be consistent.
Why doesn't the UBI file system work for you?
That is a whole can of worms for us as to why that doesn't work, but it doesn't work in our situation. It might work for some of these other issues. All right.